On behalf of NIOSH-supported education and research centers throughout the country, we're pleased to present the 2020 Ergonomics webinar series, offering free monthly webinars on various topics on human factors and ergonomics. This collaborative effort on behalf of each ERC's continuing education program aspires to provide access to current research supported through NIOSH ERC programs. So thanks for joining us today. I will mention a couple of upcoming webinars quickly. The next NIOSH ERC webinar is titled The Impact of a Scope Stand on Biomechanical Exposures During Simulated Colonoscopies. And that will be with Dr. Amandeep Shergill on Wednesday, March 25th from noon to 1 Pacific Standard Time. And our next free COEH webinar is titled The Effects of Physician Burnout on Practice. That will be presented by Dr. Carolyn S. Dua, and that will be on March 4th, 2020 from 12 to 1 Pacific Standard Time. Today's webinar is Using Anthropometry, Biomechanics, and Usability to Inform Product Design. It's brought to you by the Northwest COHS and University of Washington. And our speaker will be Dr. Pete Johnson. I will just, let me throw in a quick housekeeping note here that we will be muting you for the webinar. However, Q&A box is open, so please submit questions. We'll save some time at the end to address your questions. And also, the webinar will be recorded and archived for viewing on COEH Northern California's YouTube channel. So please like and subscribe to that channel to help us grow our audience. Thank you very much. Dr. Johnson is a retired professor from the School of Public Health at the University of Washington. He earned his doctorate in bioengineering from the University of California, Berkeley, and has worked as a researcher at the National Institutes of Occupational Health in the United States, Sweden, and Denmark. Dr. Johnson's research focuses on evaluating seating alternatives to improve comfort and reduce vehicle operator exposures to whole body vibration. Dr. Johnson's work also includes evaluating the ergonomics and usability of mice, keyboards, and tablets. Thank you for joining us. And Dr. Johnson, I'll give you the floor.
All right, Alan, thank you very much. And thanks to all of you attending. Sorry about the technical difficulties last week. I was traveling and I was in the basement of the Santa Clara Library and got a conference room. I didn't have any phone reception, but I had Wi-Fi, and I closed my email application and started the presentation and plugged in my iPhone, and it nuked the presentation on the first slide. And I ended up giving a wonderful 45-minute presentation to myself, not knowing anybody could listen. This time, I'm glad that we have around 70 attendees, and I promise the same wonderful, hopefully wonderful 45-minute presentation.
Just a sec.
Oops. So I want to talk about anthropometry, and anthropometry is
working on that. It's okay.
Getting rid of sorry. Anthropometry is a Greek term, anthropos meaning human and metrikos meaning measuring, and it's the measurement of humans. And those of you who fly a lot like me are aware that they limit the size of carry-on items. And also, if you're like me, either the seats are getting smaller or I'm getting larger because I have a hard time fitting in my airplane seats these days. With respect to anthropometry and human variability, there's 5 sources. One is age, differences due to age, gender differences between male and female, occupational differences versus an administrator versus somebody working in a material handling capacity, heredity based on where your ethnicity originates, generational. We're getting bigger generation by generation, and we used to be getting bigger in a lineal fashion, but now with the last 3 decades, we're getting bigger in a volume fashion, where our weight is certainly increasing much more in proportion to stature or length-based measurements. And there are even diurnal changes in anthropometry. If those of you who drive home wonder why you adjust your mirror at the end of the day when you get in your car. Well, your spine is probably increased in height, maybe a quarter centimeter to 1 centimeter. So all of these things are important to take into account when we're dealing with anthropometry and human variability. So differences vary, and they do matter. So here we see a 95th percentile male and female in this figure on the left portion, and a 5th percentile male and female. And ideally, what we try and do is we try and design to include everybody but the smallest 5% of the population, which is often your 5th percentile female. And we find our upper limit where we're going to end up excluding the 5th percentile of the largest portion of our population, typically your 95th percentile male, with our goal of designing so 90% of the population can be accommodated by our design. So that's what we'd like to do ideally. As far as anthropometric resources, there is a book called Body Space by Stephen Pheasant. That's in its 3rd edition, and it's an excellent resource. In it and other places on the web, you'll find information on both functional anthropometry, which deals with anthropometry during human movement. So here is showing functional anthropometry of a person sitting on the right side of the female, and functional anthropometry of the male while standing. And then also functional anthropometry in the horizontal plane, looking at the secondary reach envelope in black and the primary reach envelope in white. And you see this optimal work area in this figure here, showing that ideally we would like frequently used objects in front and centered on the user. Another great source of anthropometric information is from the Department of Trade and Industry in the United Kingdom. And they have 3 sources: adult data for adult anthropometry, child data for child anthropometry, and then they even have older adult data. And what you'll see in these tables is typically a plethora of what are called static anthropometric measurements. And these are just measurements based on the body being still and not moving. So there's multiple measurements for the hand, the whole body, your arms and legs, measurements of width and breadth. So if you can think of it, you can probably find it in one of these anthropometric tables. This is an example of hand length from the child data. So it gives you the dimension, and it's told about how it is collected, and then there's sources of the information. So this was child data consolidated from 2 populations in the United Kingdom and the Netherlands. And here is hand length as a function of age for males. And you can see you have your mean measurement and the lower or smaller 5th percentile and the larger and upper 95th percentile. And so this is for males and for females. So great resources. And basically in Excel, if you know the mean and the standard deviation, you can recreate a normal curve and figure out the anthropometry of any percentile if you desired or had the need to do that. So I had a big interest in anthropometry early in my career, looking at kids using computers and women. And I noticed kids have different size bikes that get bigger with age, and even there are differences between bikes between males and females. The same applies towards ski. Kind of the camber or carve of the ski is slightly different between males and females based on center of gravity differences. And even golf clubs come in different lengths, and the handles have different diameters based on your hand size. And for whatever reason, I can't hit the golf ball straight, so I'm sure I just must have the wrong size handle on my golf club. I wish it was that simple. And even way back in the day, this is from an archaeological dig, and they found the head of an axe for an adult. And then they thought, well, maybe they were so smart back in the day that they made a head of an axe for a younger person. So it's important, or I'd like you to think it's important to design based on the age and gender or sex of people. So initially, I was kind of curious to identify what percentage of the population was made of kids. And our definition of kids were people between 6 and, I believe, 15 years of age, because after 15, we start approximating adults. And what percentage of the population was female, and also what percentage of the population may be Caucasian. And what I'm going to present later on is your keyboard and mouse are kind of designed using the 95th percentile male as the design norm. And there's two ways you can design things. One is for reach, so everybody can get at it like a light switch. And the other is for clearance, so everybody can get through it like the doorway. And the size of your keyboard keys are based on clearance. They want to make sure your largest finger male can easily punch on those keys. And then the smaller fingered females and kids or smaller statured people can accommodate that slightly larger size. So kind of in my quest to determine what percentage of the population may be 95th percentile male, we looked at anthropometry country by country. North America, roughly 8% of the population. Europe, around 10%. So roughly, if you consider those Caucasian populations, around 18% of the world is Caucasian. 6% of the population in South America, 14% in Africa, and amazingly enough, almost 2/3 of the world's population is in Asia. So that was my first takeaway, that if you're designing something and it may be used around the world, roughly 2/3 of your population may be in Asia. If you look at children between 6 and 15 years, I thought they may benefit from smaller computer input devices. That's roughly 20% of the world's population. And if you look at the percentage of the population that are women or female, that is 49% of the population. And the reason why it's not 50% is there is a slightly disproportionate number more of males and females in Asia. So that was kind of news to me. Half the population is female and 1/5 of the population is kids, yet we're using the 95th percentile as a design norm for our computer input devices, our mice and keyboards. So I'd like to present some work of a master's student of mine from South Korea, Sean Huang, and he looked at whether there are differences between male and female anthropometry based on gender and race. And this was a small study. We just had 28 subjects, with 14 being Caucasian, 14 being Asian, and 7 males and 7 females from each of these populations. So this is a little bit small of a size really to make broad sweeping conclusions from. But what I can tell you is we've repeated this with much larger numbers, and what we found in this study for the most part will stand for a larger population. And what I was interested in is determining the mass of fingers, because basically when you type, you have to be able to rest your fingers on the keyboard. And if you can't rest your fingers on the keyboard, then you're going to always have to activate your extensor muscles, and your extensor muscles are going to get tired, and you may end up with tendonitis at the elbow. So really, I thought the resting force of mice and keyboards are probably based on the finger mass of your 95th percentile male. So we did water displacement of these various groups of subjects to determine whether there are differences in finger mass between males and females and the Caucasian and Asian populations. The other thing I was interested in was measuring just the resting force on the mouse. This was something we put a load cell under the mouse, and we could get the resting force of these different people. And probably the button activation force should be slightly greater than this resting force to provide a safety factor, so the heaviest male does not have to fear of accidentally activating the mouse button. What we found out is taking measures of length and breadth of the fingers, using static anthropometry, we could estimate finger mass with 95% accuracy. I don't have anything to show you that, but this just shows the mass of the fingers on the right hand for females. And what we found out is there were no differences in finger mass between Asian females and Caucasian females, that they really turn out to be one population. What we did find out is the Asian males were intermediate in size and different from the females with respect to finger mass. And finally, the Caucasian males represented a third population with the greatest finger mass. So what I want to dial in here on is the index finger, the finger we use on the mouse, and see what happens when we look at the resting force on the mouse button. Is it any related at all to the finger mass? So here is the finger mass from the previous slide with the females in maroon, Asian males in yellow, and Caucasian males in light green. And here are the resting finger masses. So there's probably some mass coming from the hand, things along that line causing the resting finger force to be greater. But the trends match our finger mass trends. And interestingly enough, most mice and keyboards have an activation force between 0.6 and 0.8 newtons. So you can see there's a safety factor there for your 95th percentile male, but it's probably overkill for your Asian males and females. So thinking maybe we might want to dial in our activation forces based on geographic regions and gender or sex. So I had another master's student, Janet Blackstone, do some work looking at anthropometry with adults and children and determining whether there were any differences. And what we did is we looked at anthropometry from kids from age 5 to 18, and we normalized the anthropometry and expressed it as a percentage relative to a 5-year-old child. So what we see is basically all the way up to age 13, there's no difference between male and female kids. And then roughly at about age 15, we see a split where with respect to finger length, males have longer fingers than females. But to my surprise, there's only around a 6% difference in finger length. And probably if you added in hand length, that difference may double. So don't let that deceive you. But even more interestingly, when we looked at the males in the black line and the females in the gray line, when we looked at a mass characteristic, basically the finger mass or the volume of the finger, we found 1/3 difference, where females' fingers were roughly 2/3 the mass of males' fingers. And that got me thinking, well, would that be reason to maybe have a masked a keyboard designed on at least gender, where there would be differences between males and females? And then when we look at these differences for kids, relative to being 5, there's a 50% difference in finger length and a 3-fold difference in finger mass. And so what that made me conclude, at least for males, adult males and females, is would it make sense to have a keyboard with male size keys based on finger breadth and activation forces for him, and a keyboard for females. This kind of combines all the results and kind of shows the percentage of the world population that are female, both Asian and Caucasian, being the largest percentage of the world's population. Then our Asian males are intermediate, and then our Caucasian males make up the smallest proportion. And this is showing the distribution of finger masses based on geography and gender. So this is kind of where we are today, is most keyboards have 19mm wide keys, that's called key pitch, and roughly a 0.6 Newton activation force. And if you looked at who that would fit, that really fits around 1.5% of the world's population. It's great for the 95th percentile males and larger, but it may not be ideal for smaller statured individuals based on gender and ethnicity. If we take our male population, we get our Asian male population, we get some of the 95th percentile females and 5th percentile males in there. We get around 29% of the population. And then finally, if you remember that showing the population density of females in the world, that's representing roughly 70% of the population. So we have these three different modes based on region and ethnicity. So it really makes me think, should we have three types of keyboards? One for your largest males, another for intermediate sized people in stature, where we could also reduce the key width, and then another keyboard for those with smaller stature, lowering the force and narrowing the key width. So that's where I left these things, and I think it would be interesting given how so many other products are designed based on gender and age and sometimes regionality. Why do computer input devices use this one-size-fits-all paradigm? Wouldn't it be beneficial to make these devices fit us more from an anthropometric strength and stature perspective? Going into the realm of children and even adults, this was work done by Ling Sui, another master's student of mine. And what we did is we had 16 adults and their same gender biological child, 16 children between ages 6 and 8. We had them use the mouse next to a 104 key standard keyboard, and then a reduced key keyboard where these navigation keys were eliminated. And we compared children and adults to that along with the keyboard size. And basically what we found out is going from a large to a small keyboard in adults reduces the amount of abduction or outer rotation of the arm, and it also has the same benefit for children. So smaller keyboards will bring the arm closer to the center line of the body. And then in addition, for both keyboards, the children here are working at greater amounts of abduction or outward rotation of the arm. So there's a significant difference between age and a significant difference between keyboard size, affecting postural parameters for both children and adults. Then what we did is we wanted to look at the either external or internal rotation about the elbow with adults and children using the large and small keyboard. And in both populations, we found out that the larger keyboard had external rotation of the arm about the elbow, and the smaller keyboard promoted a more favorable internal rotation of the arm at the elbow using the keyboards. And really in most environments today, even in word processing and email, your mouse is used 2 to 4 times more than your keyboard. And I think all of these extended footprint keyboards discriminate against users. And if you can forego using these navigation keys, which 2% of the population report that they need, you could get along with a smaller footprint keyboard and get your pointing device closer to you in the center line of your body. Now I want to go into the realm of usability, now that we've kind of beat anthropometry a little bit to death. And with usability testing, what we do is what I call triangulation. You try and think of 3 outcome measures and measure them and see what they indicate and see if they all point in the same direction, and you pat yourself on the back when that happens, or if you get different results from the various outcome measures. So for example, in some instances, looking at seat comfort, we look at subjective measures of comfort using Borg body discomfort ratings. We look at subjective measures of seat features using Likert ratings. And we look at objective measures of discomfort, which could be posture or EMG. Another important thing is to look at performance. So if you can subjectively and objectively measure performance, that can be beneficial to show a new design does not have much of a performance decrement relative to the old design. And then we often use desirability, where we have them rank things before they use them. We have them rank them after they use them. And then we ask for impressions comparing all the devices once they have used each of them. So this is our general rubric for usability testing. So I want to present a study I did with Dan Odell at Microsoft, where we were trying to find an improved posture for the mouse. Most of us, you know, you go to shake somebody's hand and your forearm is in 0 degrees of pronation, but yet to use our mouse, we have to go from that handshake position to putting our hand flat on the table, and that's 90 degrees of pronation or 90 degrees away from the neutral posture. And we wanted to see if we could design a mouse where your hand was not as pronated and see if people liked the design and it didn't have any performance decrements associated with it. So what we did is we triangulated on the desirability, comfort based on objective and subjective measurements, and objective and subjective measures of performance. So for performance, we had a pointing task that could get at movement times and accuracy. For comfort, we measured wrist posture using electrogoniometers. For perceived fatigue, we used a Borg CR10 scale. And then for subjective preference, we used these 7-point Likert scales. And I'll show you examples of each. We had 12 subjects use the mouse. They were all right-handed mouse users, relatively experienced, and had a mean age of 33, so not your run-of-the-mill student populations. So we had a good range of subjects with respect to age, and we had 6 male and 6 female. And the question is always going to come up, well, what should your sample size be? And that's a little bit of a loaded question. If you know the variability of the data and the difference you want to detect, you can use statistics to predict sample sizes. But sometimes if you've never collected the data, you have no information to draw from. And usually what we do is we shoot to have 15 to 20 subjects initially. And typically, if there are moderate to large differences, you will be able to detect them with your inferential statistics. I'd say the smallest I might be willing to go, if it was a single population, would be somewhere around 9 subjects. Then you're finally maybe getting rid of some of the variability where your measures of central tendency, you may be able to see some differences. So these were the mice we tested. This was the current mouse made by Microsoft at the time. And this was a commercially sold upright mouse that promoted almost no pronation. And Microsoft had 3 pronation reducing designs that they wanted evaluated. And what was neat is we were able to make these prototypes functional. We could take the engine from a battery operated mouse, and we could put the encoder in each of these mice, and the buttons were actually functional and clicked and worked like buttons. So this is about as close as you can get to evaluating real products before they are made. And this just shows us measuring wrist extension and ulnar deviation with the electrogoniometers. And then we had a accelerometer or inclinometer on top of the hand, and that could give us the amount of pronation when people used the mouse. Then the task we had them perform is we wanted them to do some sort of standardized task. So any differences we see were hopefully due to features associated with the mouse rather than features related to them doing different tasks. And we created this omnidirectional pointing task where they would start out, a circle would light up, they'd click on it, it'd disappear. On the opposite side of the circle, it'd light up, you'd click on it, and you go through 360 degrees of pointing. So we had these targets, which were the size of an icon on a desktop, to a small circle, which had targets basically the size of a character in a word processing document. And they had, based on the target size and the distance between them, the same index of difficulty. So we had small, medium, and large tasks. And they performed 6 trials with each of these different tasks, and we randomized the task and the mouse presentation order. This shows our subjective measures using the Borg CR10 scale, and we converted it into an analog form. And so this asks how much fatigue are you feeling in the right hand and wrist, and they could just mark anywhere on this line their level of perceived fatigue, and we would measure that and turn that into a continuous value. And this is an example of our 7-point Likert question, where they can choose 1 strongly disagree, 7 strongly agree, or somewhere in between. So those were our subjective measures of discomfort and feature preference. This shows the various mice on top here, and the blue line is the amount of pronation that we measured. So the baseline mouse had the most pronation, the evolent mouse had the least pronation, but you can see the pronation reducing designs of the 3 mice all had a fairly significant effect on the amount of pronation that the users had. The pink is extension, and basically all 3 of the pronation reducing designs really didn't adversely affect extension. However, there was a difference between the standard mouse and the evolent mouse that had slightly more extension. And here in green is our results for ulnar deviation, deviating to the side towards the pinky. And there were significant differences between mice, but our 3 pronation reducing designs did not look to be grave offenders. They did not cause the greatest amount of ulnar deviation, which occurred with the baseline and the upright mouse. So posture results are looking relatively promising for the 3 pronation reducing designs. These are the movement times for the various mice, and there's 2 things going on here. Is they did 6 trials, and you can see across each of the mice, they performed a little bit better with each trial. And that's one of the challenges with a short duration usability study, is they may be accommodating to a new product. And if you want to know how long they should perform to accommodate, you may be able, for example, measure pointing performance and see where it plateaus, and then you can start collecting the data. That might be the good news, but the bad news is there is a reciprocal tapping task that somebody had people perform for, I think, up to 2 months, and it wasn't until 2 weeks that he found the performance to really plateau. But what we found out is by the last 3 trials, the movement times had stabilized, and we found out movement times were slowest with the upright mouse, fastest with the baseline mouse, and really no difference between the pronation reducing models and the baseline mouse. So there is nothing screaming to us that there are problems with productivity with the 3 pronation reducing models, where people were a little bit slower with the commercially available upright mouse. And we think the reason being is instead of using your fine finger and wrist muscles to move the upright mouse, you had to create the movements with the larger muscles about your shoulder. So that's why we think there were differences between this upright mouse and all these other mice. So no movement time warnings with the 3 pronation models, reducing models. And then finally, these are our subjective Likert results, and higher scores are better. And here just shows, familiarity breeds favoritism. With the baseline model, it was significantly higher, or the highest ratings compared to all the other mice. But what we did find out is one of the pronation reducing models, Model H, typically had the second highest scores. So basically, based on the suite of objective and subjective results, we were able to somewhat conclude that Model H didn't reduce pronation, minimally affected productivity, and was the most favored among the pronation reducing designs. And so back in 2008, that's when we ended up with your Microsoft wireless laser mouse 6000. So this was a neat project where we took a very high fidelity prototype and we were able to draw what I hope were some very meaningful conclusions. Now, what I want to end with is another usability study looking at subjective and objective evaluation of 3 seats. This was done at a commercial seat manufacturer, and basically they had a prototype seat of theirs that they wanted to compare to 2 of the leading competitors. And what we did is we wanted the seats covered. We got our 18 subjects. So we didn't know the variability, but we hoped that this would just give us enough subjects to have some ability to do some inferential statistics. And we tried to get an even distribution of light, medium, and heavy drivers. And this was a US-based group. And if you're heavy, you're more than 211 pounds. And if you're light, you're less than 160 pounds. And this just shows the distribution of the weights. We have mass in kilograms on the x-axis and height on the y-axis. So we tried to create 3 distinct groups to see if there are any effects of these seats based on their body mass or BMI. So this is where we did our triangulation. With body discomfort, it was the Borg discomfort ratings. We also used seat pressure and foam stiffness, which were objective measures. We had seat comfort, where subjectively we had the seat comfort ratings, but also we could use the anthropometry and seat pressure as objective measures for comfort. And then we had our desirability, where they ranked the seats where they were blinded from the visual aspects when they sat on them at the beginning before the experiment. Then we got those same impressions with the seats covered at the end of the experiment. And then also after they used all 3 seats, they could give comparative post-use impressions. This was our overall study protocol with things we did before the study. We adjusted each of the seats to the subject's anthropometry. We kind of limited the adjustments so they could only adjust seat height, seat depth, and back angle. And they adjusted each seat independently to what they thought was comfortable. And then once we dialed in on their seat settings, they sat in this simulated cab, and we measured their seat pressure for 15 minutes, both the seat pan and the seat back. And we measured their perceived body discomfort at the beginning, middle, and end with a Borg CR10 scale in several body regions. And at the end of the 15 minutes, we measured seat feature comfort with our 7-point Likert questions. And then we closed out the experiment measuring their anthropometry and debriefed and paid the subjects. And as in all usability experiments, you want to be careful of any bias with the order of presentation of things you're comparing. So we always randomize the presentation of the 3 different seats so it's counterbalanced, so each seat is presented an equal number of times the first, second, or third time. This is kind of a global view of our experiment. So we get the pre-use rankings of which seat they like with it covered after it's been adjusted based on their impressions. Then we evaluate the first seat where we get our Borg CR10 discomfort measures at the beginning, middle, and end of the 15 minutes of sitting on the seat. At the end of the 15 minutes, we collect our Likert seat feature comfort preferences, and we had 18 questions there. And then after they've used all, after that, they give final impressions on the seat. We repeat it for the second and third seat. And finally, we collect the post-use impressions and rankings and compare with pre-use. All right, so here's an example of our question. So again, we had this Visualog analog scale using the Borg for discomfort, where they could mark on the line and we measure and get a continuous measure of their discomfort, for example, in the tailbones. Perhaps an associated other subjective measure might be the comfort of the seat cushion. So we'd have a question, I like the firmness of the seat cushion. They could answer anywhere between strongly disagree and agree and give a rating there. And then we could had a second question where we could dial in on the seat cushion firmness. Was it just right, too firm, or too soft? So using these complementary discomfort and comfort measures where you're trying to subjectively dial in on the product design. So this is the preliminary preference of the 3 seats, and basically each seat was equally desired. 6 of them liked seat A the most, 6 seat B, and 6 seat C, and associated with the other rankings. So you couldn't have a more even start to the race based on the preliminary static rating ranking of comfort. However, after they sat in the seats for 15 minutes, we could see differences. After the 15 minutes, seat B turned out to have the most rankings of most preferred and the highest average rank, and seat A seemed to be the least preferred seat. So it's interesting that you probably can't trust initial impressions, but it did look like after 15 minutes that subjects' impressions maybe were somewhat materialized, and that we got good information after sitting in the seat for 15 minutes. This is just showing the Likert ratings in different regions on the seat. And interestingly, I'm sorry, for the seat back, seat C appeared to be the most preferred with respect to seat back features. And then if we look at the seat pan features, seat C just was the most preferred in all of the seat pan features. So there really seemed to be differences in the seat pan. A lot of these did not reach statistical significance, and I think that's somewhat a function of the number of subjects we had and the variability. Had we probably doubled the number of subjects, you know, many of these differences would have been significant, but I think we had a lot to glean from based on what seats finished first and what seats consistently finished last in these rankings. The other interesting thing is seat B was a rock star with the seat base, but interestingly enough, did not perform too well with the seat back features. So that was our first indication something may be awry. So this is looking at the seat comfort again, the backrest width and the bolstering of the upper back. And we could see that with seat B, people really did not like the backrest width, and they did not like the bolstering. And if we look at seat cushion width, where seat B was the rock star, they liked the width and it was just right. Whereas the other seats did not have as high as scores, and there are more percentages or greater percentage of subjects responding that is either too narrow or the thigh support was too little. So we had some concerns with seat B again in the backrest, and we're really comfortable with what the results from the seat pan. This just shows cross-sectional views looking at the front of the seat, and seat A is in red, seat B is in bright green, and seat C is in bright blue. And you can see as far as the seat pan bolstering, seat B, the one that seemed to have the high ratings, had fairly aggressive bolstering. And then you see in the seat back some slight differences in back support, with seat C providing the least amount of lumbar support. And this is without the lumbar supports inflated. So if the seat not inflated, seat C had the least lumbar curvature. And the interesting thing we found out, since there are some problems with seat B in the backrest, it had the most aggressive bowstring. So we think that there are indications that they weren't providing enough clearance in the backrest, upper portion of the backrest for the larger drivers. And that's why seat B was not getting the favorable ratings in the backrest design. This shows our CR10 Borg scale discomfort ratings. We had 15 subjects. A mistake we made and a lesson learned is we should have screened the subjects that they were free of pain. 3 of our subjects had a fair amount of back pain, and their responses to the Borg scale were just very different than the other subjects. So due to them being in pain, we excluded those 3 subjects with pain. And if we do this again, we're going to phone screen and get their levels of discomfort to hopefully have people that are just having no or small levels of discomfort in the various body regions. And this shows the average discomfort rating over the 3 measurements, beginning, middle, and end by body location, and the change over all body parts with respect to time. So that's showing the full 10-point scale of the Borg scale. And there's something called the CR100 scale, which we've switched to, which we're using in the future. That's much more sensitive to the lower end of the Borg scale. And when we zoom in on our scale, we found out while there is some significant differences in discomfort between the body parts, and the discomfort really seemed to slightly increase and especially increase the last half of the experiment. So somewhat of a small trend with time. All right, here's discomfort measures from an area we wouldn't expect the differences in seats to matter, the feet and ankles. And this is the mean discomfort over time for seat A in red, seat B in green, and seat C in blue. And we did not see any differences in discomfort in feet and ankle discomfort across the 3 seats. So you kind of expect that. Here is a region where we did measure significant differences in discomfort. So interestingly enough, seat B, which was rated most favorably, the seat pan subjectively had the lowest discomfort rating, and seat C had the highest discomfort rating, with this difference being significant and a slight trend indicating an increase of discomfort over all 3 seats with time. So here's our third bit of information. This is showing all the discomfort results from all the body parts, and seat B is looking great until we get to the upper back, and we get this really large rating in discomfort in the upper back. So this is really what led us to realize there's something really going on with the backrest of seat B, where we may have some problems and some changes are going to have to be made to the contouring and width of the backrest. We did testing of the stiffness of the foam. So basically what you do is you put a load into the foam until you get 50 millimeters of displacement, and then you release the foam, and that can give you a measure of stiffness and hysteresis. And seat B had the softest foam. Seat C was intermediate in seat pan stiffness foam, and seat A had the stiffest foam. So we have some objective measures also characterizing the foam. And with our seat pressure results, a neat thing we were able to do is we were able to average the pressure map results over all 18 subjects. So what you're seeing here is a composite pressure map result of the average of 18 subjects. And you can visually see some differences relative to seat B in the seat pan pressure from seat A and seat C. Seat B had the largest area, the lowest percentage of hot spots, and the highest rating for seat firmness, whereas seat A had the highest high pressure area, was the stiffest, and had the lowest rating for seat firmness. And then seat C, which had the stiffest foam, had the lowest surface area and the worst discomfort rating. So a lot of these things are coming together to indicate seat B is looking favorable, but we have problems with the backrest. Lastly, we could look at the seat pressure by BMI. And interestingly enough, the people you got to worry about with respect to seat bank discomfort are your lightest subjects. They literally have the least amount of padding in their rear end to protect them from the padding. And they are the ones that would be most likely to experience discomfort due to them just not having the same amount of adipose tissue as overweight and obese people. So that was interesting. You can also see how the surface area changes by BMI of the subject. And I'm gonna, I think, quickly go to the end. So our measures indicated that seat B was favored over seat C and seat A. The seat cushion was liked by users, but there are certainly problems with the backrest of seat B. And then finally, it looked like we were lucky and all of our triangulation measures kind of pointed in the same direction. And when they pointed in a different direction, we were able to identify the problem. So I'm going to end here. Here's a picture of myself when I was a young assistant professor working on a grant. You can see I'm drinking a lot of Coke, and fortunately my 12-month-year-old son, Torben, drinking a lot of milk, but he was editing the grant figures for me. So Torben and I will open it up to questions. And I see 3 questions up here. So Alan, I turn it over to you, and I wonder if you want me to read and try and answer the questions.
Well, yeah, I'm not really sure of protocol there, Pete. I think, thank you very much, by the way. That was excellent. I was looking at your posture there while you're working on the laptop.
Yeah.
I was a little concerned about that. However, so I think I will read them and you can answer them. Of course, you can also read them to yourself for the audience sake. I'll read them verbatim, I think.
Okay.
You made reference to a couple of sources for anthropometry data, and the body space data is quite old. Size North America is conducting digital body scans to aid in clothing sizes. Is anyone conducting digital scans of the hand to quantify hand size details to confirm your research?
So that's a great point. There was an article, I think in around the year 2000, that questioned this anthropometric data. And what they found is most of the length dimensions aren't changing or haven't changed that much in the past 2 to 3 decades, but certainly all the volume measurements have. So girth, waist breadth, things like that. So I think the lineal measurements are for the most part okay and haven't changed that much, but anything related to weight or mass would be problematic, and you should have more accurate data for that. So great question.
Great. Next question is there any interest by manufacturers to design the length of mice to fit the anthropometric dimensions of the hand? Most appear short, resulting in more gripping and pinching and wrist movement.
Yeah, there's a great mouse controversy in that some people feel the mouse should fill the hand and kind of maximize the amount of pressure. And other people think a smaller mouse may be better. And it's kind of why there are 2 iPhone sizes. Is the big iPhone was too big for most of the smaller statured females, and they dropped them more. And so they made the phone smaller, so it was easier for them to grip. But that small phone is just as easy for the males to grip. And with computer mice, for me, I like to be able to manipulate the mouse with my fingers within my wrist. So I'm actually using a kid-sized mouse. And if you have a large mouse, what happens is you kind of neutralize the wrist and fingers, and you're forcing movements about the shoulder. So some of it is personal preference, and some of it, there could be reasons for using a large mouse or reasons for using a small mouse.
Okay, great. Next question. During the seat studies, did you consider longer term studies? 15 minutes does not seem like a long enough period of time to fully understand how some of the comfort and discomfort to make a decision. A seat that feels good at 15 minutes may be dreadful after 6 hours compared to other options.
Oh, what a bunch of baloney. No, that person has a really good point. is if you look at foam creep, the foam even is changing for up to 2 hours. 15 minutes, I think, is good to get a good first impression. Then there's a question, you could do longer static studies to get information on the longer term, but these seats are used in vibrating environments. So then, you know, you could introduce these seat comfort on a shaker table. And then finally, what really matters when the rubber meets the road, and you might want to really replicate this in real vehicles over the same standardized route. But each time you do that, the number of dollar signs increase. So it's often because of time and money that we do these short studies and hope that our results from the short term predict the long term. But I agree with the question, is certainly it would be a lot more robust for testing periods of time similar to what people would be spending in the seats.
Okay, the next question is, I'll abbreviate it slightly, but the questioner cannot seem to locate relevant anthropometric data on leg clearance for leg swing when pushing behind a wheeled object.
Ooh, boy, that's a good one. So that would be an example of functional anthropometry, kind of looking at the envelope of leg swing. And I don't have any silver bullets there. That's a very important measure, and maybe people have not measured that, and that's something that we should start to collect for all our warehouse workers and the various warehouses moving things around.
Great. Another question here, does age make a difference in seat comfort?
Does age make a difference in seat comfort? That is a good question. And I don't know what the answer is. Maybe some people mellow with age and they aren't as picky. And some people maybe get more particular with age, where they may be kind of more concerned about it. So I think it's probably really subject dependent, and I don't know if there's any general average trends that I could state with age, and maybe other people know, but I'm not aware of anything that I can put my finger on right now.
Okay, great. The last thing I have is a comment from a listener, and they said that Gold Touch is making a mouse now that has exchangeable parts to change the size of length to meet preference, user preference. So I just wanted to throw that comment out there. And that looks like it for the questions at this time. So I just want to throw out there that you can go to our website, coehberkeley.edu, to register for upcoming webinars. And you could also subscribe to the YouTube channel. And that would allow you to review some of the past webinars. Yeah, at this time, I'd like to say thank you very much, Dr. Johnson, for your excellent presentation, and we'll catch everyone on the next time.
All right, thanks, Alan, and thanks to all those that's stuck with it and listened to the webinar this week.
Okay, bye now.
Bye-bye.